Welcome back to the next video, everybody. Today is the first video on chapter 5 and the last video of the week. So I will see you guys on Monday after this video is posted. I'm just going to give a brief introduction to what is a finite flat group scheme. References for this chapter, other than the ones that I specifically provide throughout, will be just generally like CSS, Cornell, Silverman, Stevens, chapter 5, Bakill's book, The Rising Sea, Foundations of Algebraic Geometry, and then Hartshorn's book on algebraic geometry. In other words, I'm sort of assuming that you've been through probably a course on classical algebraic geometry and probably a year of schemes. So this chapter will try to exhibit the basic properties of finite flat group schemes, and it will culminate by describing the results about these guys that we'll need for the proof of modularity. And then we'll pick up in later chapters and actually use those results. Okay, so motivation. We'll let A be an abelian variety over a field K, and we'll let V be a discrete valuation on K with valuation ring OV. So that's just the set of objects that have non-negative valuation. Okay, we say A has good reduction at V if there's an abelian OV scheme AV, such that A is isomorphic to A sub V tensor over O sub V with K. Good reduction at V means A can be given the structure of a nice OV variety. Okay, and so what's going on is the kernel of a degree n isogeny of dimension G abelian varieties. So we've got, two abelian varieties, A and B. They're both dimension G. We have a degree n isogeny between them. It turns out that at a place of good reduction, the kernel of such an isogeny is a finite flat group OV scheme of order n to the 2G. So for example, you can see Conrad's notes on abelian varieties, chapter 4. We'll also talk a little bit about this in chapter 17 of my notes. But what's going on here is this fact right here, you could argue, is the main reason that we like to study finite flat group schemes in the first place. Okay, so what are some prerequisites for this chapter? Again, you'll want to be aware of the basic language of scheme theory. Other than that, you'll really only need to recall that the category of affine schemes is equivalent to the opposite category of rings. If you like, I have a whole set of notes on this that I can either just give you if you ask, or I can even do a series of talks on YouTube about exactly how this equivalence comes about. You can also see standard references like Bakill and Hartshorn. We will also mostly only really need to be working locally, so over affine schemes, which is great because that makes things a little bit easier. And that's because we're going to be working with finite morphisms of schemes, which are affine, preimages of affine schemes under finite morphisms are affine. And so that means we can work locally like this. And so that'll make things a little bit easier to stomach. Rings and algebras throughout this chapter will be commutative unital unless specified otherwise. Okay, so to end this talk, what is a finite flat group scheme? I'm not going to give you the most general definition. I will give you a definition that's easier to digest that applies exactly precisely to our situation. Okay, and again, I just think it's a little bit easier to think about things this way. I'm not even going to really use the word flat in my definition, actually. So if R is a Noetherian ring, a finite flat group scheme G over R is an R scheme. So if you don't know what an R scheme is, if I have a scheme S and I say it's an R scheme, that just means it has a structure mapped to spec R. Okay. And so a finite flat group scheme G over R is an R scheme of the form G equals spec A. So I have a map G to spec R. And I require that A is a commutative hop R algebra. In other words, I'm sort of saying that I want G to be an R group scheme. Okay. And the catch here is the whole flatness, the whole finite flat thing. That just means that A is a locally free of finite rank R module. Okay. So I'm going from spec A to spec R. Okay. And this guy is like an R group scheme. And then I'm assuming A is a locally on spec A free of finite rank R module. That's all that's going on here. And we'll talk about Hopf algebras later. In fact, because of this definition, we will be interested in developing the theory of Hopf algebras more generally. Okay. And then I'll just end by making a comment here. The theory that we'll treat in this chapter is on average a little bit more general than what we actually need. But I'm always in favor of more generality. And okay, so I will see you on Monday, and thanks for watching.